All right. Well, welcome to the first of oh, a very small number of me talking over. Well, in my case, it's Keynote, but PowerPoint. Slides with words on them. Um, Try not to do this. I'm not too terribly crazy about it, but I have these slides from last year, and I'm falling behind. So we're gonna push ahead. Um, um, so we're going to talk about, and I've rearranged the slides. So we're going to talk about causal loop diagrams. This is the first um, uh, set of tools that we're going to develop, and it's focused on causal relationships. A causes B, which may cause C. And they'll get, actually, by the time we're done here with this little chat, we'll look at a reasonably complicated causal loop diagram. But I want to start, we're going to talk about, we've talked about toilet bowls. You should have read about thermostats. So we've done a little bit of housing infrastructure, the kinds of things that we're familiar with. Hopefully all of us are well housed. And today we're going to talk about chickens. There are a number of idiomatic kinds of things in our culture, and I think even those of you who have spent significant time in other cultures probably are familiar with some of the crazy chicken ideas. So we're going to talk a little about chickens here in just a bit, but first we're going to talk about ice cream and murder. It has been observed that in the summertime, ice cream sales increase, and that's taken as an indicator that we humans eat more ice cream in the summer. It's also observed that the number of homicides goes up in the summer. As a former New Yorker, I can tell you that both of these are particularly true in the place that I call home. It's probably more of a phenomenon. Number of you who are from the Chicago environs would probably recognize this as true. And from this, we might conclude that, in fact, eating ice cream causes murder. And we would represent that in a causal loop diagram in the following. So you can see here, let's see, get my cursor going. So if we were to look at this set of graphs, we would say, okay, well, these two are related, and maybe ice cream sales. You might say, well, that homicides cause eating ice cream, but it's probably more likely that if there was a causal relationship, it would go the other way. And so in a causal loop sense, and I'm going to go into more of this diagramming here shortly, you would say ice cream sales cause murder. So as ice cream sales go up, murder goes up. As ice cream sales go down, murder rate goes down. But then again, maybe it's the heat, because look, here's a schematic diagram of temperature, average temperature, daytime temperature, overnight lows, however you want to look at it. Basically, it's cold in the wintertime. I've tried to get this about right. It gets hot in the summer. It's really hot in August and September. It's probably starting to cool down a little bit more than I have drawn here in October. And by the time we're back to January, it's cold again. So maybe it's the heat. And in causal loop form, we would draw it like this. And these diagrams, again, are from, well, not again, this is actually for the first time, Sturman, the book that I've mentioned a couple of times, but have not yet pointed you at. In the causal relationship of this correlation here is that it gets hot in the summertime. And when it's hot, people eat more ice cream. So as average temperature goes up, ice cream sales go up. And they get irritable. And unfortunately, that leads to the number of homicides going up. So a correct causal relationship here is that as it involves a third uh, element, and that is the average temperature. This is very important. It is often very tempting to do things like this. But it's, as Sturman has pointed out, incorrect. In causal loop diagrams, we need to be very disciplined about what causes what. And be very careful not to confuse correlation with causation. That's true in general, not just with silly examples from a business textbook. All right, so that's murder and ice cream. Let's talk about chickens and eggs. There is, of course, the classic conundrum of why did the chicken cross the road? And we're going to think about that here in just a minute. But before we do that, there's in some ways, I would say, a more primary conundrum around the chickens, and that is which came first, the chicken or the egg. And I've previewed this diagram in one of the earlier videos, but I'm going to go into a little bit more detail now because there's a little more detail here. So this actually has a feedback loop. So now we know that while we may argue about which came first, and this diagram certainly doesn't solve that problem, it is clear that more eggs causes more chickens. You need an egg to get a chicken. So as the number of eggs goes up, so too does the number of chickens. And that's what this little plus sign means. It means that when this one increases, this one increases. And when this one decreases, this one also decreases. So it means that they have the same polarity. And that's what we call this. We call this polarity. As eggs go up, chickens go up. If eggs go down, chickens go down. Similarly, as chickens go up, eggs go up. So as we get more chickens, we get more eggs. They go the same way. So that's what the plus sign here is. As chickens go down, fewer eggs. So this doesn't mean that things get bigger. It means that the two things that are connected by this arrow change in the same way. And that's a very important thing that will be a little hard to get used to. I can tell you A, from my own experience, and B, from the experience in other classes. Now, so we've got the arrows. These two are connected in a causal way, and the polarity of that causal relationship is positive. And there's a feedback. Eggs goes up, chickens goes up, eggs goes up. And that's so the cycle goes around in this direction, and this R means reinforcing. If I had a, I probably could learn how to do it, but this R is reinforcing. I would like to write it right here, but I don't know how to do that. A system's feedback structure generates its dynamics. Okay, and so we'll get back to that. But let me, so this is a reinforcing loop. In an infinite world with infinite chickens and no death, well, the chickens wouldn't be infinite right away, but you would just keep getting more chickens and more eggs. You'd get really tired of bacon, egg, and cheese, et cetera, et cetera. Systems generates its dynamics. Okay, now dynamics here refers to the behavior of the system over time. So here's time on the axis. In some sense, let's see. Maybe we do try to answer the which came first, the chicken or the eggs. Of course, the problem with that conundrum is, are you talking about a particular chicken or are you talking about chickens in general? So what this says is that at any given time, the number of eggs is less than the number of chickens. Um, and it says that they both increase in this sort of exponential way. Now, let's see. What in my notes it says? So there's a relationship between chickens and eggs. That's it. Draw arrows. What's missing? Yeah. What's missing from this graph is some scaling on here. I guess it's inherently it would be number, and you could have and there's some implication that these two are related. If I were doing this, I would say number of chickens on one over here and number of eggs over here probably have the same relationship, but the graph could be a little bit clearer. But a really important part, let's see what happens, whoops, of this is that the system's feedback structure, that's this whole thing, it's a reinforcing loop, generates its dynamics, which is its behavior over time. Right. Right, I think I've beaten that one. It's positive feedback. What's wrong with the graph? Okay, I've done all that. So let's see what the next one is. So another thing that chickens are famous for doing is crossing roads. It has always been a bit of a conundrum as to why the chicken crosses the road. The answer to the riddle, of course, is to get to the other side. Not a very satisfactory answer because it sort of leaves out any intentionality that the chicken might have had regarding the road in economic terms. If we have economic man, if we have economic chicken, it's likely that the chicken crosses the road to increase its utility function in some way or another. There's always some implication that there's something on the other side of the road that the chicken wants. All right, that's enough of that. Chickens and roads. Okay, so here is a slightly. It looks the same, doesn't it? Well, except that chickens is on the other side of the diagram. So in this one, we have a relationship between chickens and road crossings, and it says that as the number of chickens goes up, so too does the number of road crossings, and implied here is road crossings by chickens, and that there's some probability function associated with the the act of a chicken actually crossing the road, and that's positive. But so chickens cross, as you get more chickens, you get more road crossings. Now, chickens, while they may have some intentionality in crossing the road, they're not necessarily very good at it. And so that as chicken road crossings go up, in fact, the number of chickens goes down. And that, the rate at which road crossings going up and chickens going down is going to be some function of traffic and chicken density and chicken road crossing skill. But you'll notice here, so chickens going up, road crossings going up, same sign. If chickens go down, we'll come back to that. That's the balancing part. So we get the plus sign here. You'll note here we have a minus sign. So what that means is that as road crossings go up, chickens go down. So if you could see me, you could see that I would be pointing up with the index finger of one of my hands and pointing down the index finger of my other hand. And I'll demonstrate that at some opportunity in Studio B. So this is a negative polarity. That is, the relationship, the causal relationship between road crossings and chickens is opposite. If road crossings go up, chickens go down. If road crossings go down, chickens go up. And again, our good friend John Sturman has gotten more economical with his words, but the behavior of this structure, so structure, system, chickens and roads, has the following characteristic. And whether they would actually go to zero, and you know, same comment about axes labeling and all that sort of thing. But as if you don't get any more chickens, I guess if you don't get any more chickens, there's going to be some asymptote, because at some point, if I'm sorry, but you know, if we assume maybe chicken road crossings is simply a Brownian motion, and it's just a random thing that happens. Maybe there's no intentionality in it at all. I would expect that this would go to some asymptote. Sturman is saying that eventually the last chicken crosses the road and gets hit by a truck. We can argue about what happens out here in time, but the point is that the structure has a particular dynamics associated with it, which he's now calling behavior. All right, blather, blather. Let's now talk about this B, because in the previous diagram, there are two plus signs, and we have a positive feedback, and things always go up. In this system, we have a plus sign and a minus sign. And going one way around, chickens and road crossings go up. Going the other way around, chickens go down. So there's a negative. I think of this as a negative feedback, and clearly the decline here is a decline. And so this is called a balancing loop. When a loop has an odd number of minus signs, we'll get into that more later. So we have one minus sign, an odd number. So chickens go down here. It's a balancing loop, a negative feedback. And we're gonna come back to the chicken example here in just a few slides. But that's the basic structure of causal loops. In the simplest sense, you have a thing. If it increases, if it has a causal relationship with another thing, and that relationship is such that thing A, thing one, hearkening to well, it's not good in metaphor. I was trying to make a Dr. Seuss joke. Chickens go up, road crossings go up. That's a positive causal relationship, and then a negative causal relationship. All right, next slide. Introduce it to the grammar. I've kind of already gone over this. Here's a lot of words saying more or less what I've said before. If X goes up and Y goes up, then it's a positive polarity. You don't worry about the mathematics. Here's words that say the same thing. And here's a few examples. If product quality goes up, sales, we expect sales to go up. Holding all, and somewhere else it says here, all else equal. And that's a very important element. And if effort goes up, results go up. If you work harder, you get either better results or more of them. Similarly, if births go up, population goes up, all else equal. And then there's the negative polarity. All else equal, if X increases or decreases, then Y decreases or, and this is the math. It's just got a negative sign here. Don't worry about the details of the mathematics. If product price goes up, sales go down. As frustration goes up, results go down. As death goes up, population goes down. So like I said, this is a lot of words, but this is the core of the grammar in causal loop diagrams. Well, there's one more bit, and I think we get to it in the next slide. So So I said that this is the core. Uh, these symbols are very important. Your causal loop diagram is not very useful if there is no polarity. This just says there's a relationship between sales from word of mouth and customer base, and the customer base, but it doesn't say whether these are positive or negative. So it doesn't really give us any information. It just says that there are these, we believe that there are these causal relationships. But now, if you add polarity, sales from word of mouth goes up, customer base goes up, customer base goes up, sales from word of mouth goes up. All right, so this is two pluses. They're both going in the same way in this, then, and it's a reinforcing loop. All right, so, and they're all coming into customer base. Customer base here is so this one actually we could customer base. So as customer base, let's just start here. As customer base goes up, customer loss rate goes up. I will leave it to some of you all who are studying consumerism and all that sort of thing to tell me whether that's the right. Is it the rate that goes up or the number of customers that are lost? I don't know the answer to that. And as the customer loss rate goes up, the customer base shrinks. So this has got a going up and a going down part. So it's a balancing loop. There's some ambiguity here about rate versus number. And so that gets at the importance of choosing these words very, very carefully. But now we've made a slightly more complicated causal loop diagram, which has two loops in it, a reinforcing loop that makes the customer base go up, and a balancing loop where the customer base goes down. And of course, the balancing between the weighting on how fast these things go up or down is going to determine the actual change in the customer base. Similarly, so I'm not going to go into this a lot, but here's a little exercise as quality. Well, actually, we will. We'll run through this quite quickly. So this just says that there are asserted causal relationships among these characteristics and product attractiveness. I would say that as quality goes up, product attractiveness goes up. So that would be a positive. You'd put a little plus sign here. As price goes up, product attractiveness goes down. So I'd put a little minus sign here. Let's do another. As delivery delay goes down, product attractiveness goes up. And so again, we'd have a minus sign here because down and up and down. So they're the opposite. And then finally, as functionality goes up, product attractiveness will go up. And I guess if I was going to do this consistently, I would say as functionality goes down, product attractiveness goes down. But they're the same, so you get a plus sign here. All right. So back to chickens and eggs. Here is a challenge. Sturman is great. He's got all these little challenges. It's nice he includes at least one rooster in the chicken population just to keep things going. But so here's the same basically the customer base loop. Oops, kind of push C. The customer base loop only with chickens, eggs, and road crossings. As chickens go up, eggs go up, chickens go up. As chickens go up, road crossings go up, chickens go down. Chickens go down, eggs go down, chickens go down. So we've got a reinforcing loop here, and we have a balancing loop here. For some reason, this little diagram just makes me happy. But you can see how we've now brought together the two things and how we can start to build larger collections of these causal loop diagrams that start to be more informative than simply just the chickens and the eggs and the chickens and the road crossings. All right, and now we go back to product quality. The product quality examples and well, I guess there's a coffee example in here. I'm surprised I would have forgotten that. And so he says the point here is that there's a bit missing. As product quality goes down, quality improvement programs go up. Well, is there a direct link between product? Well, and then let's just finish the loop here. As quality improvement programs go up, so too does product quality. But is there a direct link here? I mean, it's a balancing loop, but product quality going down doesn't directly lead to quality improvement programs. Similarly, the coffee temperature and the cooling rate are not directly related. And so now we're starting to introduce some external parameters. A better loop here, according to Sturman, is that as product quality goes down, the quality shortfall goes up. That is, there's some target quality that we're looking for, and as the product quality goes down, the difference between product quality and the desired product quality, so this goes down, minus sign, so down, up, quality shortfall goes up. So it's actually quality shortfall. So as quality shortfall goes up, quality improvement programs go up. So it's quality shortfall that leads to the increase in quality improvement programs, which in turn bring up product quality, which then reduces quality shortfall. So as quality improvement programs go up, product quality goes up, and the quality shortfall goes down. Similarly, with coffee, it's really the difference between the coffee temperature and the room temperature that drives the cooling rate. That's a bit of physics. I don't think anybody, one of you, and I'm not going to make a guess as to who it is, but I know at least one of you has an engineering bent. A number of you are thinking about renewable energy. This is just physics. That the cooling rate is really has to do with the temperature difference, not with the actual temperature of the coffee. Right. So now we've brought in an external factor to our loop. And I would call this a parameter. I'm not sure whether Sturman would go that far or not. So the loops are getting now again more sophisticated. All right, so let's talk about grades, causal loop diagrams and grades. I talked very briefly in the early going about my philosophy of starting at 0 and adding points rather than starting at 100 and subtracting points. And the thinking that I did that led me to that a while ago had to do with coercion. Which way did the coercion... I tried to eliminate coercion, but I realized it's all part of the deal. And we're inside some coercive framework, so I couldn't get rid of it entirely, but I could shift it more to my liking. But this is basically a diagram of coercion. I've used a minus sign here instead of a B. So sometimes instead of a balance, let's get to that. So let's start at the likelihood of a desired grade. Uh, um, as the likelihood that you or I, because I worry about my reviews and how well I'm doing, as the likelihood of a desired grade goes up. Or let's do it the other way, because that's often the case. It's the likelihood of a desired grade goes down. That is, I'm falling away from my self-imposed expectations for a grade. Fear goes up. So this is going down. This is going up. This is a minus sign. So they have opposite sign. So as likelihood of a desired grade goes down, my fear goes up. As fear goes up, I'm more likely to take action. And if I take action, the likelihood of it, my desired grade goes up. So this is a balancing loop. As this decays, things happen that work against that decay. And it's a coercive structure. It has fear in it, which is too bad, but it's the way of the world, I guess. And it's a sort of a basic motivation, and maybe this reveals more about my own psychology than yours. So we can make a causal loop of our motivation to work. And Sturman, so this Sturman goes into some detail about all this. And this is one of his diagrams. Well, I think we're going to go into some of these in more detail later on. But let's see. Where should we start here? So let's start with schedule pressure. Let's see, what do I want to do? I didn't study this one as much as I might have. So this is actually has more of a production element to it. But anyway, have schedule pressure, and as that goes up, there's more overtime in production. As overtime goes up, completion rate goes up. As completion rate goes up, work remaining goes down, and schedule pressure, completion rate goes up, work remaining goes down, schedule pressure goes down. And there's an external parameter here called time remaining. And that he calls that the midnight oil loop. So this brings in one final element of these loops. When you start to make these bigger diagrams, it's very useful to give your loops a name. So he's called this one the midnight oil because you're doing more overtime in order to have a balancing loop. And by adding a number here, he indicates there's likely to be more than one balancing loop in the system. In fact, here's B2 called corner cutting. And that's the key there is going to be here. As schedule pressure goes up, time per task goes down. We get sloppy, we spend less time doing things well. As time per task goes down, productivity goes down. So we have a negative polarity arrow here. As productivity, wait a minute, goes down, completion rate, that's not right. Schedule pressure goes up, time per task goes down. Time per task goes down. Oh, right, this is a negative arrow. Productivity goes up. As productivity goes up, completion rate goes up. Work remaining, blah, blah, blah. So that's called corner cutting. That means you're not doing as much work. And then he has a reinforcing loop where overtime causes fatigue, which reduces productivity, which reduces completion rate, which increases the work remaining. And you can follow these around. The other thing he's introduced here is that there's delays. You can put delays into these loops. So overtime doesn't immediately cause fatigue, but if you carry on with overtime for too long, you get more fatigue. Right. And you can follow. I encourage you to spend a little time looking at this diagram. I will put these slides up on the Canvas site. Let's see. Your variables need to have names, and they should be nouns or noun phrases. They shouldn't be verbs. So completion rate is a noun. Work remaining is a noun. Fatigue is a noun. It's very important that these be nouns rather than verbs. The loops need to have a clear sense of direction. So the loop goes around like this. And then Sturman encourages to choose variable names whose normal sense of direction is positive. So productivity we think of as a positive thing. Completion rate we think of as a positive thing, etc. And then finally, as I pointed out, give your loops names. This is kind of jumping ahead a little bit, but this is the kind of thing. This is the kind of analysis that we're getting toward. Right. Questions, please send them to me in email, and I will respond to them. And I will look forward to giving you some more material to look at. All right. Over and out.